All right, multivariable, Miss Deer back here. Sorry, my document camera / phone died. So let's do this problem again, but let's do it with Stokes' theorem. So I believe that my surface was a sphere. So z is rad 1 minus x squared minus y squared, and my field was x squared. What was it? Oh, where was it? Well, where's my field? Oh, here we go. Negative, oh, that's not even close. Negative y plus z I hat, thank you, assistant, plus x minus z j hat, plus x minus y k hat. So in order to use a surface integral, we're going to need to create a function. So let's call our function of x, y, and z x squared plus y squared plus z squared minus 1. So now we can find a normal vector. So our normal vector is 2xi hat plus 2yj hat plus 2zk hat all over the magnitude of this vector. So we're rad 4x squared plus 4y squared plus 4z squared. The 2's are all going to cancel with the 4's. And x squared plus y squared plus z squared is 1. So this just becomes xi hat plus yj hat plus z k hat. Now we need to find curl f, which is what we're going to dot with this normal vector. So I have I hat, j hat, k hat, my del operator, the partial with respect to x, the partial with respect to y, the partial with respect to z. And then I have the components of my field. So I get -1 minus -1, 0 I hat, 1 minus 1, 0 j hat, and 1 minus -1, which is 2 k hat. So now I need to take the double integral of my surface, and then I have curl f dot n, so 0 times x plus 0 times y plus 2 times z ds. And remember that this isn't particularly useful with a ds, so we're going to have to solve for ds is going to be the surface dz. So I know that z is rad 1 minus x squared minus y squared. So the partial derivative of z with respect to x is 1 over 2 rad 1 minus x squared minus y squared times -2x. And the partial of z with respect to y is 1 over 2 rad 1 minus x squared minus y squared times -2y, which gives me 1 rad 1 plus the partial with respect to x squared. So x squared over rad 1 minus x squared minus y squared plus -y squared over rad 1 minus x squared minus y squared. So let's turn these into z's. So I have 1 plus x squared over z plus y squared over z, which is, let's make a common denominator, z squared. So, no, z. Whoop. All right, so what do I get? I get, so z, oh my gosh, let's clean this up. So zx was -x over z. zy was -y over z. So ds is rad 1 plus zx squared plus zy squared. which is rad x squared plus y squared plus z squared all over z squared, which is 1 over rad z squared, which is 1 over z. Whew. All right, so now what am I going to do with this? Let's go back to my double integral, which was I had the double integral over my surface of 2z ds. So now I'm going to turn this into the double integral of 2z times, well, ds is going to turn into 1 over z dA. And the area is of a circle. So this is the double integral over the region of 2 dA. And I could definitely go polar, but I know that this is the area of a circle of radius 1. So I have 2 times pi times 1 squared, which is 2 pi. I'm not gonna lie, I don't remember what we got before. Did we get 2 pi before? I'm just gonna believe that we nailed this because a lot of algebra happened in the middle. Whew, all right. So two ways, one